So next, let's go through some basics for AI. We'll talk about concepts, data, and the common algorithms. So overall, if we think about it, as again, when we say AI, we're talking about numerical AI, we're talking about machine learning here. So when we are talking about machine learning, so what do we have in machine learning? So how can we have different components? And one common way to do that is to view machine learning as an ensemble of three things. First, representation. Second, solution. Third, evaluation. You may not be able to find this in some textbooks that don't talk about this. So first, what is representation? That is how we organize the data, the knowledge. Then when we say, so that, in other words, that's what the model looks like and how knowledge is represented. That's the first thing. That's algorithms. Second is something called a solution, or in other words, optimization or solver. Many people say that. That is when you have the knowledge, you have the X and the Y. You know how to get X to Y, right? You know the algorithm. However, you need to find the exact route to go from X to Y. And there's an infinite number of routes that can help us do that. So which route is the best? And that will determine what the eventual model will look like. So the algorithm just tells us how to get the model, and the data will help us to determine what exactly the model look like. And the solution, solver, optimizer, they're just the things that help us to get that. Evaluation, when you get a model based on the algorithm and data, then how tell is the good one or not? One thing that I need to mention is that actually many people believe that it does not make too much sense to talk about models without referring to data. You have data, you say, oh, my model is perfect. Many people say, does not make sense because you don't talk about data. Your model may be good for one thing, but it may not be good for another thing, right? You said, I developed one model for autonomous driving. Then you use it for weather forecast, maybe not, right? So that's one thing. But we also have to admit that many models, they have wide applicabilities. They can be applied to a different task. That's why people are always interested in the narrow AI or the general AI. That's why people are interested in general AI. Evaluation is the part how we can evaluate an AI algorithm or a model. And there are different criteria can be used for that, depending on what tasks that you want to look into. So first, representation. Let's see how we can organize the knowledge, the method. And there's a few concepts that we need to know about. First, this data. And for data, we have something called input and output. I'll give more information about that. Here, I just read through them very quickly. So the input variables, features, so these represent the input data that you need into machine learning models for mathematical equations in order for it to learn the parameters, the coefficients, and make predictions about the output. They're also called dependent variable. In engineering, if you know the partial differential equations, you will know something called dependent variables and independent variables. Independent variables, X, Y, Z, T. Dependent variables are the thing that you want to solve. For example, stress, strain, displacement. And concept 1.2, that's output variable. That's something that you need to figure out. For example, that's the Y. And this is also called the dependent variable or the response variable. And this is the variable that we want the machine learning models to predict and estimate. And again, input variables features the input. Third one is something called algorithm. So algorithm, that's what we used for solving different types of problems, such as regression, classification, and clustering. They tell us how to get from X to Y. It's one way of thinking. Usually, if you say, what the algorithm look like, you possibly have seen something called a pseudocode, right? It's not a real code, but tell you, what do you initialize something, then you do the first step, second step, do loop, using a conditional statement, something like that. Right? Then, depending on what computer language that you are using, you're gonna implement the pseudocode in different ways. So algorithm is something like that. And third is mathematical model or function. As I said, no matter most of the problems that we're dealing with can be visualized as a mapping, right? Mapping is a function. Function here, that's actually the model. And no matter you're talking about physics-based engineering methods or AI methods, we are all trying to get a model, a mapping. And if we do it strictly using math language, then we are trying to get something that's built up on math, right? This in the simplest case, if you do the curve fitting, it's just like a curve fitting function, second order polynomial, right? That's very simple. But we know that linear regression cannot help us solve real world problems. For example, you want to do the object detection. It's hard to do it using no matter how many orders of polynomial that you want to go, it's hard to do that, right? In that case, how to do that? That's why people look into deep learning, the neural network. It has multiple layers. Each layer has multiple neurons. And for each neuron, you have the activation, right? You have the weights. You put all of them together, you create a super complicated curve fitting function. And we don't know what exactly the function look like, but it's a function, right? Give us the flexibility to deal with the real world problem. So that is the mathematical model. That is the function. Parameter, coefficients. So that's when you do the model, you have the neural network, you have a lot of weights, and so that's the things. And in addition to these parameters associated with the model, we also have something called hyperparameters. Hyperparameters is not something that will determine your model, but it may be something, for example, associated with your solver. How you can fix, sometimes you need to fix something to set up, you need to assign a number to something so you would tell the computer how to arrange the solver, how to run the solver. So those are the hyperparameters. Then solution. So when we go to the solution solver optimization, so if you have ever taken any courses relevant to optimization before, you will hear terms like loss function, cost function, objective function, all of these different terms. They may mean the same thing or may mean slightly different things depending on the context. It's very confusing. But in a simple way, you can imagine, they're very similar things. We have this because when we're talking about optimization, we need to optimize something, right? When we do optimization, there are two ways. You either try to minimize it or you try to maximize it, right? Depending on, for example, loss function. Loss is the bad thing. We want to minimize it. Cost function, we don't want a high cost, so we want to minimize it. Objective function, that's more general, right? We can either maximize it or minimize it. So they can be very similar. And one way to construct loss function, of course, you use something to predict something, right? You predict that, and then you compare your prediction with the true solution or the labeled object. I'll talk about that later. You see the difference. The big difference. That means, your model is really bad. You need to make some changes to it, right? And if the prediction is pretty good, acceptable. Then you say that, optimization is done. So that's the loss function. And the construction, the selection of loss cost objective functions usually is one key step that will determine whether you can get a good model and how good your model is. And finally, we have the optimization algorithms, methods, or solvers. Some people say that. So there are many of them. You can do it using an analytical method. One common one is the gradient descent. And these days also, we need to use stochastic gradient descent a lot. We also have adaptive learning method, traditional conjugated gradient methods. New methods include the derivative-free optimization, zeroth order optimization, and meta learning. So just get an impression of these things. You don't need to know the details at this moment. It's okay. Evaluation, that's another key thing. Different evaluation metrics are used for different tasks. We will talk about tasks in the coming slide. We do classification, regression, clustering. We just talk about what good the model is and what mathematical equation can be used to better describe that difference. So for a classification, we have the common things that we would use include confusion matrix, recall, sensitivity, and specificity, F1 score, AUC, and ROC, and also logarithmic loss. For regression, those things maybe you're familiar with. The root mean squared error, RMSE, the mean squared error, MSE, the mean absolute error, MAE, and R squared. And those things, and it's not difficult. You possibly have used these things in some other courses before. Finally, for clustering, We have different sample data, so we want to group them into different groups. And for this one, for example, we can use the random score and adjust the mutual information. Now let's take a look at data. This is one of the most confusing thing when you start looking into machine learning. So if you have a difficulty in realizing what is data, just take a look at this. Think about it, what do you have in, for example, Excel spreadsheet. When you try to put data into it, you have rows, you have columns, right? So we can do it in this way. Each row is kind of one data point. For example, if you're talking about the coordinate of one object, you have x, y, and z, right? That's kind of each column, x, first x, second y, third column, z, right? Then you have different points. Point 1, 2, 3, so you give it an ID 1, 2, 3, 4. And for different point 1, 2, 3, each of them, we would have x coordinate, y coordinate, and z coordinate. But in real applications, we not just have 3, sometimes we have more than that. And they're not associated with coordinate, but with some other attributes of the thing that we are analyzing. And for each sample data point, there are different names. They're interchangeable. So pay attention to this. And if you take a look at the reading material, those book chapters that I share and will share with you, you will find that we use many things interchangeably, and it could be confusing. Even different chapters may use different words because they may be contributed by people from different disciplines. And for example, we have used samples. It's the same thing. One sample means one row, all the way from here to here, excluding the rightmost this column. So everything here from the first column to the second rightmost column, they are called X. And the rightmost column here, you see the class here, that's the label, that is called the Y. So for big X 2D matrix, in this case, each row in it is called a sample data point or an observation or an instance. Very confusing. All of them means the same thing. And if we take a look at every column represents one attribute or one feature of one sample. Attribute feature is the same thing. And here, this called attribute, the name. And here's the attribute value here. And then we go to the rightmost column. We would see the Y, that's the output. We call it label or target. It's the same thing. And for each sample, it has its own label. Sometimes it would label, you may have 2 different values, 3 more. But in this case, we only have 1, so there's only 1 column, but there can be more. And if we combine, if we have 1 sample that is labeled, then we would call it a labeled instance, a labeled sample, a labeled observation, or some people call it one example. That means it's labeled. So this is how to look at the data. Again, the confusing part is the terms. And then how to use data in a typical engineering machine learning process. First, collect and prepare data. So actually this part, if you really use machine learning to solve a problem, you will find that in many cases, the majority of the time will be spent on this. If you got data, if you know how to use like a machine learning package, get it done within minutes. But you find that you spend a month just to collect and process the data. That's the reality. It's pathetic, but that's reality. And we use data augmentation. Sometimes you got a lot of data, for example, image with different sizes. You need to cut and crop all of them, make them into the same size, time consuming. Data augmentation, sometimes you don't have too much data. You need to play with the data, add some noise to it, so that's data augmentation. Then if you have a supervised learning task, then you need to label the data. That's another pain in the ass. It's very, sometimes you have a lot of data, but they're not labeled. If you want to do it supervised learning, I can give you one good example. One trick that Google uses is that you possibly all have got this experience before. When you log to a website, Google asks you to tell what do you have in that image. Or let you say that, do you have like hydrant in that image, something like that. In that process, Google wants to test whether you are a robot, right? We do that. But the smart part of this is that Google used your input to label the image. It's very smart. So that's one way to get labeled data. Anyway, second step is to either choose or develop a machine learning algorithm. Second, so if you think the problem could be solved using an existing one, don't bother making one yourself. Just use the existing one. If you find that it's not good enough or it's not suitable for your application, then you possibly need to develop your own, either from scratch or by modifying the existing one. The third one is to train the model with the algorithm using the training data. So you have data, algorithm, then you get the model. So model is the thing with all the fixed weights, parameters. That's the model. And then you evaluate the model using testing data. So here you see another concept, training and testing. If you are not familiar with machine learning, that's another confusing part. That's actually mostly associated with supervised learning. You got to label data. You need to look into data, try to extract the model. Then you want to see whether the model is good or not. So usually what we do is that, for example, you have a big pool of data, you divide it into two parts, either 50-50, 60-40, or 70-30. For training, 64% for training, 40% for testing. They need to have the same, something called distribution. Here we are in engineering, so we don't talk about that too much. They have the same distribution and they need to be drawn in the same way. They're not the same thing, but from a probability perspective, they're the same. They can represent the real data. Then you use the 60% training data to get the model. Then you test the model using the remaining 40%. Some people call it testing. In some disciplines, they use word cross-validation. Maybe they have slightly different meanings, but in a simple way, you can understand it in this way. Then you evaluate the model using testing data. Next, if you're not okay with the performance, the results that you got using your evaluation metrics is not too good, then you can fine-tune the hyperparameters to improve the model. Do the training again to see if you get better results. So many people say that for AI, you need to spend a lot of time on it. It's weird. You do all the fine-tuning thing. It's like an art. Many people even say that. Last, after you get a improved model, you can make predictions for new data samples. These new data samples, they're not from that big pool of data that I just mentioned, from somewhere else. For example, in supervised learning, they're not labeled. They do the prediction. You don't know it's good or not, actually, if you don't know the correct answer because they're not labeled. And learning types and the tasks. These can also be confusing. First, learning types. So in a simple way, we can divide the machine learning algorithms into three big categories: supervised learning, the unsupervised learning, and reinforcement learning. Of course, we also have something called semi-supervised learning, but in this course, we will not talk too much about that. Then another thing is that you know what types of machine learning algorithms that you have, then is how you can use it. So that's what type of task you want to apply your machine learning model to. We have regression, we have classification. That's easy to understand, right? Regression, you have points, you want to get a continuous curve to pass through all of them. Classification, in using data language, we just want to get different categories, which category that data, that sample belongs to. But if you use a math language that we want to put it into, instead of give it a continuous label, we give it a discrete label. For example, you can either use a text. For example, if this is a bad, good, or something between medium, right? Or sometimes to facilitate the coding, we may use 1, 2, 3. But we know that 1 is for good, 2 is for bad, 3 is for medium. And we also have some other things, tasks that are not that common. We have, for example, dimension reduction. We have anomaly detection. We have ranking, and we have recommendation. And if we take a look at the relationship between tasks and learning types, we'll find that machine learning, as I said, three major categories. For supervised learning, we usually use algorithms from this category for regression and classification. For unsupervised learning, one typical task that we would do is clustering. We try to group different data points. And another type, dimension reduction, we will also cover this one in this course. For reinforcement learning, this one is usually used for decision making. Under which condition, which decision will give us better outcome in the long term. So we can use it for control. Another thing is for learning. I mentioned that ChatGPT, as I said, they use 2 steps to train that. First step, supervised learning. Second step, they use reinforcement learning, try to let the agent become smarter and smarter. And here for supervised learning, classification, regression, as I said, one easy way to differentiate these 2 types of tasks is to look at it from a mathematical perspective. For classification, we have discrete label or targets. The why, they're discrete, they're not continuous. And for regression, they have continuous label or target. You have numbers. And what machine learning algorithms are more popular? It's hard to tell. And this is a very dynamic area. The answer is also changing very fast. So here's one survey result conducted by Kaggle. Kaggle is a very famous platform. You can go there and do a lot of competition, get a lot of data. And based on their results from 18,996 respondents, they got this. You can see that the most popular one in 2020, linear logistic regression thing, linear models. Second, decision tree, random forest, same related. Then the third one is the convolutional neural network. So there's one popular architecture in deep learning. Then we have gradient boosting machines. So that's ensemble learning, combine different things together. Then we have Bayesian approaches based on statistics. We have next recurrent neural network. That's another architecture in deep learning. Dense neural network, that's the regular deep neural network, and some other things. And you will take a look at the topics that we will cover in this course. And you can see that here are left the weeks. You will see that first 2 weeks, we're looking into the preparation knowledge that we need to get for talking and implementing AI machine learning. Then we have linear models, decision trees, support vector machines, artificial neural network, ensemble learning, deep learning, dimension reduction, clustering, reinforcement learning, value-based reinforcement learning, and policy-based reinforcement learning. You can see that 5 of them belong to supervised learning, 2 of them belong to unsupervised learning, and 3 of them belong to reinforcement learning. So that's what we're going to do in this course. I think I'm falling for you.